This is Chapter 1, Lecture 1, The Nature of Geology. We have a few goals for this chapter, and the first is to introduce the relevance of geology to your everyday life. We will introduce the Earth's main components and systems, and using several places, we'll consider geologic processes and landscapes, and investigate how geology affects living things in those places. So let's look at North America and the surrounding ocean floor. I'll ask you, looking at this, what features do you notice? There's a few key things to note here. Toward the west, we have an area of high elevation, the Rocky Mountains. We have Mount St. Helens. We have a lower interior portion of the continent. And toward the east coast, we have the Appalachian Mountains. The east coast also has a pretty extensive shallow water area offshore. That's the continental shelf. And the continental shelf is part of the continent. It's the outer edge. There's some deep sea areas further out. And there's these east-west lines in the Pacific Ocean on the other side of the continent. And I'll also note that this is a pretty flat, low-lying area characterized by a lot of wetlands. We have the Everglades National Park marked here as well. So this is purely observational. Over time, we get into interpretations and explanations for what we see. We'll jump to this. How does geology influence where we live? Well, this is a block diagram, so you can see a cross-section into the Earth's subsurface here and the surface of the Earth. We'll kind of go one by one. I'd say some of these slopes are far too steep to build anything on. If you do, it's going to move down over time with gravity. You don't want to live in an area where landslides are prevalent because you're going to end up in the pathway of one. You obviously have to look out for volcanic eruptions. And areas with earthquakes that are located along faults where there's movement, you would have to be careful about living in those areas. The type of soil is also important. In areas where a river may flood, sometimes that can bring nutrients onto the floodplain, and it ends up being good for farming, not unlike the Saginaw River. But streams are also a flood hazard for structures. In a good way, they're a water supply. So they're good for life that way. And of course, soil nutrients. So we'll look at this scene, and by now you may realize that every image I have in these presentations is typically from the book, unless it's one of mine. So you can always reference these in more detail in the book. But yeah, we'll look at this. We have living things pointed out here as horses and cows. Let's think about the processes going on and how the geology influences the life of these horses and cows. First off, there's snow in these mountains. It provides water for the cows and the horses in terms of runoff, usually into reservoirs. We can assume that the groundwater is fairly high in this area. Well, not always in a mountainous region, but we'll just say it is here, because you can see how green that area is. So it supports life that eats vegetation. We'd say in general they're nicely protected from wind due to this section of rock. And we have constant new soil development because there's erosion coming off the rock and tumbling down the mountain. let's think about natural resources in terms of stuff that's mined and used in our societies. So this diagram is showing you locations of iron mines in blue versus copper mines in orange. And we're missing the UP copper mines. That's all right. I'll just point out that, yeah, there is copper mine here. Pretty large deposits of copper found in the western North America area. But most iron mines are in the Great Lakes region and Canada. Let's say most copper mines are in the mountainous western part of North America. And we really don't have iron or copper mines in the southeast or south central part of North America. And the reason for this with iron is that most of them formed in the Canadian Shield. That's kind of what we have outlined here. At a specific time in Earth's history, we're talking about 2 billion years ago, during an increase of oxygen in the atmosphere. And then most of the copper mines are much younger, say 50 to 150 million years ago. And those are related to events that formed a mountain belt along the west coast. Pressure from this area led to that. There's no large iron or copper mines in the southeast because the region doesn't have the appropriate type of rocks or geologic history. It's as simple as that. The distribution of resources is controlled by geology, such as age and the type of rocks and the geologic history. We should also note that those iron mines record changes in Earth's early atmosphere. Look up banded iron formations if you're not familiar with that. They're really cool. You can find them in the Upper Peninsula. All right, let's look at Australia. There's a lot of differences in, say, the texture that you see. That's changes in elevation. Simply put, our planet is divided into continents and oceans. This continent has an area of mostly smooth, shallow seafloor surrounding it. That's the continental shelf. And I said before, continental shelf is the outermost edge of a continent. It's part of it. Parts of the seafloor around Australia are complex. Parts of them are kind of smooth. And the reason for that, simply put, is that the continents and the ocean basins have different geology, different materials, and different geologic histories that made them this way. Let's note that the boundary between brown and blue and green is the current shoreline. Like right here. And we have the continental shelf in lighter blue. So keep in mind, different histories lead to different features, right? Let's look at this scene. This is a section of rock. There's a few things going on here. We can think about what's here and possible events that led to the creation of this formation in the past. And we can also think about what might happen to it in the future. So, observing an upper brown cliff at the top. There's a cliff that exposes tan, brown, and yellowish layers. We have a few blocks perched on the edge of the cliff. Ooh, I didn't want to go forward. Let's talk about that. First, we had a series of events. These were actually volcanic events that deposited the rock in these beds. That was the past. What we see now is mostly erosion. So this block perched precariously on the cliff is just going to keep falling down with gravity. We're going to see more jointing and separation of beds with more erosion over time. It's easier to answer questions about the present. Like I can tell you right now, everything's eroding because I'm looking at it. But it's harder to say what happened in the past without using other pieces of knowledge in geology. And it's also hard to say what's going to happen in the future. Although I can assume more erosion. We can't say exactly when this rock will fall, but I'm pretty sure it's going to happen. All right, moving forward. These diagrams show ice, like a glacier, 28,000 years ago to mostly present. So the point here is that 28,000 years ago, there was a lot more ice. During the last ice age, major ice age, Earth was colder than it is today. So we had ice sheets that covered a big part of North America, but also Northern Asia and Europe. Climate warmed during the past 15,000 to 20,000 years. Those ice sheets melted back, right? And they continued to disappear over time. Don't really see that stopping at the moment. All right, we'll jump to paleontology, the study of fossils and past life. This scene is an artistic interpretation of life in the Jurassic. A lot of people like Jurassic Park. Here you go. So, what types of evidence could dinosaurs and other creatures leave behind? It's not just bones or teeth fossils, it's also footprints or burrows. Now, bones tell us about the internal framework of the living thing, but footprints, track ways, those can tell us about the weight, how the organism walked or ran, whether it moved in a pack. Burrows are left by creatures that were digging into the dirt, such as earthworms. Those are hard to preserve in the fossil record, but we use those as trace fossils. They give us more evidence of past life on Earth. But what is inside Earth? Let's start, not stop, at the top here with the Earth's crust. Perhaps you've heard of that. Well, we divide it into continental crust, which is much thicker, and then oceanic crust. And those are on top of the Earth's mantle. So continental crust is compositionally different than oceanic crust. You have more lightweight minerals such as quartz, feldspar. You get something like granite from the solidification of that crust. Oceanic crust, darker, heavier minerals. This is basalt with holes in it. We call that vesicular basalt. The thickest layer of this planet is the mantle, and we have the upper mantle. That's mostly composed of a green mineral called olivine. The lower mantle is similar in composition to the upper mantle, but it has minerals that form at very high pressures. In the core, that consists of metallic iron and nickel. That's something we know based on earthquake data and observations of meteorites. We've got a molten outer core and a solid inner core. If you want, you can draw and label this to sort of cement it in your mind. Not a bad idea. You can pause the video, do that. Or you can use the notes. But looking at the Earth's layers, some of them are stronger than others. The upper layer, we call that the lithosphere. It's stronger than the asthenosphere. The asthenosphere is hotter. It's weaker. It's mostly solid. The lithosphere includes continental and oceanic crust and the uppermost strong part of the mantle. If you want, you can draw and label a sketch of that. Now, why are some regions higher than others in elevation? This shows our continental crust and our oceanic crust. Continental crust is much thicker than the oceanic crust, and the continental crust is higher in elevation. So regions with continental crust are going to be higher than oceanic crust. And regions with thick crust are higher than those with thin crust. The thickness of the crust determines the elevation of a region. The oceanic crust is thinner and denser. It's compositionally different than the continental crust, so we see it well below sea level. It can have some smaller mountains, including volcanic islands, built on top of that crust. They might not have thicker crust beneath them. Thinking more about why some regions are higher in elevation than others, just based on density and thickness alone right now. So we'll look at the relationship between the height of each block. These are wood blocks, and its thickness relative to other blocks. Some observations include that thick blocks are higher out of the water than the thin blocks. The thick blocks have more thickness beneath the water, and the block on the right is lower, so it might be kind of a different kind of wood. Perhaps it's denser. This is analogous to the Earth's crust riding on the mantle, except the mantle is not a liquid. This is explained by isostasy, and that rebound based on thickness and density explains most of the variations in elevation that we have on Earth from one region to another. It's affected, isostasy is affected by both the thickness and the density of the crust. We'll jump to another concept here. Let's think about what forces and processes affect Earth's materials, either from the inside or the outside. So this is a block diagram again. We're looking at a cross section of the Earth, and then we're looking at the surface of the Earth. Atmospheric pressure. That is actually greater at sea level, like right here. The sun and the moon both exert a gravitational pull on the Earth, but the moon exerts more because it's closer to Earth. Electromagnetic energy, when the sun's energy and cosmic rays radiates from the sun. Blowing wind moves sand and dust and makes waves. Ocean currents move water and redistribute heat across the planet. Earth's gravity causes a downward pull on Earth materials. So water, ice, and rocks move downhill. And then the weight of overlying rocks push down, countered by forces pushing up and from all sides within the Earth. Radioactive decay produces heat, and then heat can be transferred from hotter rocks to cooler ones, such as near molten rocks, and we call that magma when it's under the Earth. If it's extruded out of the Earth, we call it lava. Let's think more about the atmosphere, kind of in terms of the hydrologic cycle. And starting with water vapor, that can include drops of water and ice crystals. The atmosphere includes a low percentage of water vapor, most of which is evaporated from the Earth's oceans. We have wind, which moves water vapor around. We have clouds that are composed of small water droplets or ice crystals. We have evapotranspiration from plants. They take up moisture and they release water vapor into the atmosphere. And then evaporation with liquid water on the surface. It can evaporate and become water vapor in the atmosphere. Once condensed, it can come back down as precipitation. Land and sea absorb heat from the sun. And the atmosphere blocks sunlight and ultraviolet rays. Got it. Light from the sun passes through the atmosphere to be absorbed by Earth. Some of that sun's energy is converted to infrared. Some light that strikes Earth is converted to infrared energy. And we'll stop there for today.